Let's consider this differential equation here. Y double prime plus y equal to 0, where y of 0 is equal to 0 and y prime of 0 is equal to 1. Let's suppose the Laplace transform of y is capital Y of s. So we don't currently know what this is. The transform of y prime will then be sy of s minus y of 0, which is 0. And the transform of y double prime will be equal to s squared y of s. This term here will be 0, and then minus the initial condition of the first derivative, y prime of 0, which is 1. Our differential equation says y double prime, so we have s squared y of s minus 1. It then says plus y, which is capital Y of s, is equal to 0, and the Laplace transform of 0 is just 0. So we have this equation here. We can rewrite this as s squared plus 1 times capital Y of s equal to 1. And dividing gives me y of s is equal to 1 over s squared plus 1. So now I have a solution in terms of s, but we need one in terms of t. We originally took the Laplace transform, so now we need to do this inverse Laplace transform. So I want the inverse transform of s squared plus 1. And essentially what this means is the Laplace transform of what is equal to 1 over s squared plus 1. In order to figure this out, let's look at a table of Laplace transforms. Here I have a table, and as a reminder, I'm looking for the transform of 1 over s squared plus 1. And we can see we get that right here, where b would be equal to 1. That would give me 1 over s squared plus 1 squared. So this would be sine of 1t, or just sine of t. So this tells me that this inverse transform is sine of t, which gives me my solution. Y is equal to sine of t. So I have my solution to this differential equation. And I want to check my solution. So we had the solution y equal to sine of t. I want to check this using other methods. With a homogeneous second order, we start by getting the characteristic equation. For this one, we have r squared plus 1 equal to 0. Solving would give me r is equal to plus or minus I. So in this case, alpha is 0 and beta is 1. My general solution then looks like e to the alpha t times c1 cosine beta t plus c2 sine beta t. Since e to the 0 is 1, I can simplify this to c1 cosine t plus c2 sine t. We're also going to look for the derivative to find our c1 and c2. This is minus c1 sine t plus c2 cosine t. My first initial condition says that y of 0 is equal to 0. So y is equal to 0 whenever t is equal to 0. This would be c1 times cosine of 0, which is 1, plus c2 times sine of 0, which is 0. So I have 0 is equal to c1. My next initial condition says that when t is 0, y prime is 1. So this would be minus c1 times sine of 0, which is 0, plus c2 times cosine of 0, which is 1. So rewriting the solution, I would have 0 cosine t plus 1 sine t, which is exactly what I claimed it was before. So this gives us an idea of what the inverse Laplace transform is.